Can you hear me?
Yes, sir.
Fine. So look at look, I have done up to position 5.6. Okay. Now theorem 5.7, it's immediate in a sense. Okay. So actually you have, I guess you have done a special case in undergraduate. So suppose you have this x tau to a real valued function on a topological space continuous. Okay, and suppose A is compact. Because we assume non-empty, because empty set is always compact. So that, oh no, suppose the whole thing, I'm doing this thing. Suppose this space itself is compact. Okay, right? And of course, what? Oh, I see. Wait a minute. I'm doing in Jan, but anyway, this is house drop. And using bijection, that means one-to-one correspondence. That means it is one-to-one and onto. Look, this is continuous bijection. Okay. Then F inverse exists from the space to this. This as a function exists because bijection. Okay. So conclusion is that F inverse is also continuous. Look here, what I'm doing, domain is compact, range is house drop, and continuous bijection. Special case, what you're supposed to do, at least know, in B.Sc it is like this. By Hein-Borel theorem, also it can be proved directly that this is compact in the real line. It is compact. So if you take a real valued function here, so this is house drop. So this is compact. Here you are taking the usual distance metric. And suppose you take a one-to-one function, injection, one-to-one function. So it will go to its image. Okay. One-to-one function. In fact, you can see its image. If you use Hein-Borel theorem, FAB, this is compact. So by what I did last time, this is compact in R. So by Hein-Borel theorem, not Hein-Borel, it is directly because the metric space, it is closed and bounded. By intermediate value theorem, this has to be an interval also. That I will do after I teach you a little bit of connectedness interval. So this has to be an interval of this form, in closed bounded interval. Okay, so that it will be actually function. That means if you have a continuous, you don't need to assume this. If you have continuous function, its image has to be of an interval. Now if it is 1 to 1, that by this, then you will get a function if it in 1 to 1. I have taken the image, so it is on to. Then you will have this function, and this is saying that has to be continuous. Okay. Well, let me give an example, a geometric example of this. Let me tell you this. What is simple example? Suppose you have this. You take the interval 0 to 1. You take fx equal to x. So this will be just what will be the inverse will mean. So function is this. This is your function. So what will be the f inverse? So actually f here is going from 0 to 1 to 0 to 1. Let's say I have given one of the simplest examples, identity function. But its inverse will be what? Look, its inverse will be also this, so until again an identity function. But inverse will be what? Here this is x. And you are getting like fx here. But on the other hand, that means if you have this fx, this is y, then this will be the domain of f inverse. Then you get this value. Okay, right? This is the simplest example because this is happening with essentially it is compact, not only for the identity function. Okay, but if you don't take identity function, I can take something like, let me tell you what you can do. You can take strictly increasing function. Okay. If you take strictly increasing function, you like what you can do. I can take this, can take this. Yeah, this is should be like look, this is so this you take here. This is by hand model theorem. This is compact. This is like this. This is a continuous function, strictly increasing. So it is 1 to 1. So your range is this actually. Okay. So on that you get if this is your f inverse is domain is this, and you are getting this. Still it is continuous. Okay. It is continuous. So that is the special case. Now the proof is very simple. It is basically sort of corollary. So that look here, what will do? First of all, you see f inverse. F inverse, its inverse as a pre-image. It is f. So that f inverse, if you take a closed set, take C, closed set. Remember in the equivalent characterization of continuity, inverse image of a closed set is closed. Because here I am taking not open set, I am taking closed set because closed set related to compact sets. Because every compact set in a Hausdorff space is closed. So f inverse C, look, this is, I'll have to prove this is closed in Y sigma. Okay, because here the function f inverse and C is closed here. But inverse of inverse, this is simply F, C. Now C is closed. X is compact. Last time I did. Closed subset of a compact set is compact. C is compact because X is compact. But since it is Hausdorff, continuous image of a compact set is compact. So this is compact. So whole thing is C is compact. So FC is compact because F is continuous. But a compact set will be closed if it is Hausdorff. So this is Hausdorff given. So this is closed. So you are getting this is closed. So that equivalent criterion. This is continuous. Okay. This is so simple, but it applies how many results? Actually, it applies to look 3 results. So you are taking equivalent criteria of continuity to show it is closed. That is first thing. Then you are using continuous image of a compact set is compact. Second thing. Okay. And any compact set in a Hausdorff space is closed. So 3. So you are using 3 properties. So that's why you should look at the proof very carefully, though it is very simple. Okay. Right. Now, look here, page 160, that what we are planning to do. Okay, so that let me tell you first that compact subsets in a metric space. I have given you the definition of compact set, but often we do not prove that some set is compact or not by using the definition. Particularly compact subsets in a metric space, there are several nice characterizations. First of all, you see in a metric space you have got many things sequential characterizations. Like under the sequential characterization, look how what you got. First of the closed sets you got. Remember that. Before that you got a closure point. Okay. Because you saw that if X belongs to A bar, if and only if A is a subset of a metric space, Xd is a metric space. If and only if there exists a sequence Xn in A such that Xn goes to X. You got continuity to have this metric space function between two metric spaces. And if you take this, then F is continuous, then F is continuous at X, if and only if Xn goes to X implies, here I should write if and only if actually. Those notation are there. If and only if Xn is in X implies Fxn goes to Fx. Sequential characterization of continuity in metric space. So in Y. So you got a closure point. This don't forget. In totally bounded sets also you got totally bounded sets. Remember that. You got the sequential characterization. That means if A is a subset of X, Xd is a metric space, then A, of course you can assume A is non-empty, then A is totally bounded if and only if every sequence in A has a Cauchy subsequence. Okay. So in fact, any important concept in metric space, you have always some sort of sequential characterization. Now the question, so that we can ask the question, this question. Is there any sequential characterization Sequential characterization of a compact subset in a metric space. Of a compact set in a metric space. Question. Answer is yes, and it's a very powerful technique. In fact, often, but its proof is not easy. But don't forget, but don't bother about the proof. Thing is that it's a very powerful technique, powerful result, and you should always try to use the first one. In fact, Heinz theorem these days people use by using this sequential characterization. But that is not an elementary proof of the Heinz theorem, because to prove sequential characterization we need to do a lot of things. But if you use Heinz theorem, it becomes simpler. Anyway, so sequential characterization, powerful technique. So that basically, look here I have written. Now we go back to compact subset in a metric space. In fact, there are two nice characterizations. One in terms of sequence, other one in terms of accumulation parts. In fact, the sequential characterization of compact subset in a metric space is a very powerful and useful tool. In order to present these characterizations in a simpler way, we first present several lemmas. Okay, so that let me discuss the lemmas. Okay, first thing that you have done, I think, but it's very simple that. Let's start with it. In fact, channel topological space. Says if you take U open and F closed. If you take the difference U minus F, look, U minus F actually U intersection X minus F. Okay, because these are the points in U which are not in F. That means those points in U which are as well as in X minus F. That I am taking. Now F is closed, so this is open. The intersection of two open set is open, so this is open. But if you change this thing, then what will happen? Though it is not in the part of the lemma, then look, this will be, so this is closed. This is closed. Intersection of two closed set is closed, so this will be closed. So if you are taking difference, it depends on which one is first. If open is first, this will be open. Okay, intersection will be, this difference will be open. If the first one is closed, then difference will be closed. Okay, right. If then U minus F is, so it follows that every finite set in a metric space is closed. Particularly if you take a finite set, that means look, you have this, every finite set is closed, so this is open. If U is open, that means in any open set in a metric space, if you chop off finitely many points, still it will remain open. In fact, I have taught you T1 space. T1 space means, remember that if every point that in X tau is closed. So every finite set is closed. So T1 space, every finite set is closed. So this is what I am doing for lemma 5.2 metric space. That is true for any T1 space. Okay, any T1 space. If U is open, F is finite, then this is open in any T1 space. T1 space means every singleton is closed. So that why I am doing it? Okay, this lemma 5.3. Okay, look, lemma 5.3. This is very important. It is not true in Yale topological space. Okay, actually it will be true in a T1 space, but I am doing in a metric space. So look here, what you have got in a topological space. If you have topological space, look, what is the importance of lemma 5.3? A is a subset of X. Let's assume, and X belongs to X. Then by definition, you look, X is an accumulation point of A if every open set, if for every open set, that neighborhood of X, every open set U containing X, we have it intersects A in points other than X. That means U minus X intersection A is non-empty. That means intersection points other than X. But look, in this definition, there is no guarantee it will intersect A in infinitely many points. I know only the intersection is empty. That means basically I am guaranteeing 1 point. Okay, I do not know whether the intersection will have more than 1 point. But in a metric space, this intersection will have to be infinite. That's the thing. Look, if and only for every open set U containing X, U intersection is infinite. Okay. If of course if U intersection is infinite, then nothing to do. Then of course you know it will intersect in points other than X. Okay. For the converse, use lemma 5.2 because for lemma, you look this. For X is a metric space, then U minus X. Now look, it's not equal to empty. Okay, so suppose, look, this is non-empty. By induction, you'll have to do it. So you choose Y1. Okay, now you take U minus Y1. Now look, Y1 not equal to X, so X belongs here. Okay, so this is the neighborhood of X because this is open. So that U minus Y1 is the neighborhood of X. Okay, minus X other than X intersection A not equal to 5. So you take Y2 from here. So Y2 not equal to Y1. Of course, Y2 not equal to X. So this way you will get continue by induction. Okay. So you will get infinitely at least a sequence. Okay. Of distinct points. Okay. Which will come from A. Okay. Actually, I have done it that you can also see that word. That is an accumulation point if and only if there is a sequence of distinct points coming from A converging to X. You could use that also. Okay, you could use that also, but that proof is actually this proof. So that it will be an accumulation point. So that now that means what I am trying to say in the lemma that if you have this, if you have this thing, that X is a metric space, A is a subset of X, X belongs to X, then X is an accumulation point of A if and only if every open set, and only for every open set U containing X U intersects A in infinitely many points. That is, U intersection A is an infinite set, is infinite. Here this way it comes. It is basically true for any T1 space. In general, it is true for any T1 space. So if you have accumulation point for any open set, it has to be infinite. If it is finite for some open set containing X, if it is finite, then it is not an accumulation point. That's it. It's not an accumulation point. Okay. Look here, this I did, but you could use this also. X is an accumulation point, but that the proof is basically same. Accumulation point of A if and only if there exists a sequence xn of distinct points. That's the way we have produced actually sequence that way, simply that way. So proof is basically same. Distinct points in A such that xn converges to X. So that if you take any open set containing X, so that will contain a tail of the sequence, but the sequence has distinct points, so that it will contain infinitely many distinct points. Understand? But the proof of this result, or what I was giving by using lemma 5.2, is the same. Okay. So that particularly you should understand, if it is for one open set containing X, if it happens to be finite, then this is not an accumulation point. Now, look, lemma 5.4. Okay, I have given lemma 5.4, all these lemmas, chota result I have given you, so that big result, apparently your proof will be simpler and smaller. Okay, now look here, that X is a metric space, A is be a non-empty compact set, then A is totally bounded. Every compact set is totally bounded. Basically, lemma 5.4, that let XD be a metric space, hypothesis. XD is a metric space at A is compact. This is your hypothesis. Then A is totally bounded. But a totally bounded set need not be compact. Example is that any bounded set in R, like this. First of all, any compact subset will have to close, so it is not compact. But it is totally bounded. Reason is any subset of a totally bounded set is totally bounded. Okay, so closure of a totally bounded set is totally bounded. So this is totally bounded. So it will be totally bounded. Okay, this is actually you use this thing. Compact subset is totally bounded, and Heinz-Moral theorem. So this is totally bounded. Okay, or else you can use straight that in the real line. Bolzano-Weierstrass theorem. Every bounded sequence has a convergent subsequence. So every bounded sequence has a Cauchy subsequence. So here any sequence you take that will be bounded, it will have a convergent subsequence. So this is totally bounded. Okay, by Bolzano-Weierstrass theorem. And this is not compact because it is not even closed. You don't need Heinz-Moral theorem here. Okay, now, but we are saying every compact subset will have to be totally bounded, but not the converse. Okay, be careful. Well, remember that proof is very easy. Okay, the totally bounded, I recall the definition. Proof is easy in the sense, just use the definition. Look, totally bounded means what? That if you take any R, A is totally bounded. So there exists points x1, xn in X or A. I told you, it doesn't matter. Such that A is covered by this. Well, So you take this. A, you see that A is covered by this. The index set is A. Look, if I take any X belongs to A, that is here. So A is covered by this. Okay, but each open ball is an open set. So it's an open cover. So B XR X belongs to A. Here I'm using A as also an index set. Is an open cover of A. Since A is compact, so it will have a finite subcover. It has a finite subcover. Finite subcover will become what? Finite index. Actually, there exists X1, X2 in A. Straight we can prove. So that since A is compact, so there exists X1, X2, Xn in A such that this is the proof that actually I have written. So A is totally bounded. So any compact subset is totally bounded. Okay, got it? So any compare. Let X may A be a non-empty compact set, then actually usually people prove the corollary. Every compact metric space is separable. Okay, look at the corollary. Lemma 5.6, I said that. Well, what lemma 5.5 I am telling you. We are having a metric space. Is a non-empty compact set. I am saying there exists a countable subset of A. Countable. Such that B bar equal to A. That means closure of B is A. So in particularly if you take X is compact, that means if you use this result countable, then it will be separable. So in particular any compact result, this is very important. Basically this you need. Every compact metric space is separable. Okay. Okay. So let me see that. Okay, let me prove this first. This same proof you can also use here. So just let me tell you that how to prove that every compact metric space is separable directly, because often these people are asked prove this. So let me do that. How will you prove that every compact metric space is separable? Directly. Well, that means I'll have to produce so that take XD proof, XD compact. Okay. Now choose N belongs to N. Okay, right? I'm giving the direct proof of the corollary. Okay. Now, for this, you choose the radius 1 by N. That means, look, then Bx 1 by N, X belongs to X is an open cover of X. But XD is compact, it will have a finite subcover. Don't confuse with the same N. So it will have, here the index set is X. That means finitely many x will be there. Still those balls will cover that. So that since xt is compact, I am doing it for n. So I should be able to track n. So there exists a finite subset. My index set is x. So finite subset fn of x. That means finitely many points I will get here. Suppose you are getting this x1, x2, xk. That I am calling fn. This may not be the same. Okay, fn such that I will have this x is union b x 1 by n, x belongs to f n, fn. Okay, fn. Okay, right. This you do for each n. So that now take f equal to union of fn. That these are the basic things what I did in the beginning. Look, each fn is finite, so it is countable union of finite sets. So this is countable. Okay, it is actually will be countable infinite if you assume x is infinite. It can't be finite. Anyway, it will be countable. Countable union of finite sets is countable. My claim is that f bar equal to x, so that x is separable. Well, you take a point, any, what I'll have to show that you take any point, any ball that must intersect f. Okay, right? But okay, first of all, choose m belongs to n such that 1 by m less than r. Okay, fine. Well, so that let me see that if you got here, you are taking any x belongs to x, bxr, open balls, choose m belongs to n such that 1 by m less than r. Now look, bx 1 by m. How do you use this thing? Okay, right? Well, remember that here I got x union, don't confuse with this x. So I am writing different notation. Y 1 by n, y belongs to fn. This I got by using compactor. So y belongs to fn. Okay, so that, okay, right? Now look. Well, x 1 by n. Okay. Now x, this x. Okay. I don't need that. Okay, let me see that. What it x belongs to x. So you take n equal to m. Okay. Got it? For m, I chose 1 by m less than r. So you are taking that. This I got previous page. 6. That means so that there exists y belongs to fm such that x belongs to b y 1 by m. Okay, right? Now look, I'm done. This means right, because dxy less than 1 by m, so this belongs this. Now look, y belongs here. Okay. And y also belongs to fm. Okay. But fm is a subset of f. So that y belongs to f intersection this. But this is superset of this. That exactly I needed to prove. I have shown. I have taken any arbitrary x, took any open ball containing x, and I am showing f intersection bxr is non-empty. That precisely means f is dense in x, but f is countable. So that this is this. Same way you can prove the lemma actually. Okay, right? Well, now, so that every compact metric space is separable. In fact, look at the whole proof where I used compactness. Look, I was using this thing. This cover. Okay. And it will have a finite subcover. But if you look at totally bounded definition, given any R, X will be covered by this if X is totally bounded. Okay. Some finitely many points will be there. Okay. So that, look at the entire proof. I have actually proved this. Every totally bounded metric space is separable. Look, after using compactness, I was getting balls. Those balls, finitely many balls, that I will get also by using the definition of totally bounded. So actually, I proved this. Every totally bounded metric space is separable. But every compact metric space is totally bounded. Okay. That I proved. Okay, before. Lemma 5.4. So actually, I get this. So that automatically every compact metric space will be separable. Actually, I proved this. Okay, right. Now 5.8. Okay, before this, well, position 5.8, I'm explaining that now, but I think you can read the proof yourself to understand, because I have given all the lemmas. Okay, so what I'm saying if you have a metric space and we take a sequence of distinct points, that means xn not equal to xm whenever n not equal to m. So this we call a sequence of distinct points. Whenever n not equal to m, xn not equal to m. Okay. Now, so that A, to take this set, it has to be infinite because distinct points you have taken. Look, if you do not insist on that, then A as a set may be finite. Okay, may be finite because I can have 1, 2, 1, 2 like this sequence. So then A will be only 1, 2. As a set, A will be 1, 2. Okay, but I have taken distinct points. Okay, so here I am saying that if has a accumulation point, then there exists a subsequence xkn of xn such that xkn converges to x. Look here. Now I'm saying if x has an accumulation point, then there exists a subsequence of this converging to this. Okay, right. Look here, we'll say I am getting infinitely many points. I will get a subsequence, and that x is a closer point. So automatically it will be distinct. But the problem is that with this, I will only get a sequence coming from if x belongs to a bar in an accumulation point. If look, if A has an accumulation point x, I will get a sequence coming from here converging to this, but there is no guarantee that will be a subsequence of this. So don't think this proposition 5.3 is trivial. I am insisting there exists a subsequence. Look here, if x is an accumulation point A, so I will get a sequence coming from here converging to this, but that sequence may not be a subsequence of this sequence because it may come haphazardly. Okay, but here I am saying it's a subsequence. So subsequence is very important. Okay, so that's how you choose. Again, that means ensure that each time you are choosing, you are only moving to the right. So that is the real problem in that. Okay, it's not simple. So make sure you read the proof. Next time I will do it, and that you understand that it has to be done by induction. Lemma 5.3. Okay, that exactly I commented also. Proof by a previous result you immediately get a sequence from A converging to X, but that may not be a subsequence of Xn. In order to have a subsequence, you need to be careful about our proof. Okay, so that is the importance of the result. Okay, so that I will give you later on, but make sure that you understand the importance of the result. Okay, now theorem 5.9. This is actually okay. So theorem 5.9. I will talk about the proof of theorem 5.8, but you should prove it. You should read it. Okay, let me write. Read the proof carefully. Okay, right. Now, theorem 5.9. Look here, I am saying, suppose you have a metric space and suppose A is an infinite subset. Look, I told you in a metric space, if you have an accumulation point of a set, okay, then every neighborhood of X will intersect infinitely many points of A. So that A has to be a necessity. Because of necessity, it has to be infinite set. So let A be an infinite set if A has an accumulation point. Look here, what I'm saying, any finite set in a metric space can't have an accumulation point. There's already what I discussed about the accumulation point. Okay, because every neighborhood of an accumulation point will intersect A infinitely many points. But if you have a finite set, obviously it cannot happen. So finite set cannot have an accumulation point in a metric space. So that you need to assume infinite set. That I have assumed. Suppose it has an accumulation point, then every sequence in A has a subsequence converging to a point in A. Okay, converging to a point in A. Okay, right. Well, this two all actually I'm leaving it to that. Make sure that what I am saying that if I have to assume that any infinite subset has an accumulation point, suppose that infinite set, and suppose it has an accumulation point. Every infinite subset, A is infinite. Of course, A is infinite. That will have to assume because I am saying hypothesis is this. Suppose every infinite subset of A has an accumulation point. In A. That not only accumulation point A has, this is in A. This is very vital. Okay, every infinite subset of A has an accumulation point. Conclusion is every sequence in A has a subsequence xkn, every sequence xn. So xkn so converging to a this is important. If you have this, you have this. Okay. Well, if you do not have this, you still will have this, but you may not have this, because then I will consider a bar. A bar will be also infinite set. So every infinite subset will be an infinite subset of a bar. And then a bar will have, of course, accumulation point in A will be an accumulation point A bar. So it will be there. So I can replace A by A bar. But that means if you miss this, you will miss this one. Now look, every sequence has a subsequence converging to a point in A. So again, look here how I am doing it. Proof is a bit tricky. That means you'll have to. Problem is that I told you while defining subsequence and that. Here you'll have to ensure that you can pick up a subsequence. You can maintain that you are always picking up the elements moving to the by moving to the right. And that is the thing I am doing it. Okay. So that is the argument, and that is the induction is coming. Okay. So make sure again you read the proof. I will do it whenever if I find time. But the thing is that is very important. Now look, in immediate corollary is that if you have this, at least this has to be, then A has to be totally bounded, because every sequence in A should have a Cauchy subsequence. But here I am having a convergent subsequence. Even if it is not here, still it will be a Cauchy subsequence. So it will be totally bounded. Now, look here. Why I am doing it? So theorem 5.8, 5.9, proof is due. Proofs are due. I don't know. If I find time, I will do. But I have written everything very carefully here. Okay. Right. Well, I will be back in 10 minutes, but theorem 5.10, okay, this is very important. Let me tell you that. This, so when I take a break, you read that. This is actually not only gives sequential characterization of compactness, it gives another characterization in terms of the accumulation points. Okay. Like every infinite subset of A has an accumulation point. Okay. So that here the characterizations, this theorem 5.10, sequential characterization of compactness and that. Okay. So that where I give the problems in that. Let me tell you that. Okay. So that I will talk about this. Okay. I will be back in 5-10 minutes. Hello, you can hear me? Hello? Hello?
Yes, sir.
Yes, sir.
Okay. So I am going to this theorem 5.10. This is very vital. Characterization. Even if you do not know the proof, it's fine. But you need to, while dealing with compact subsets in a metric space, you need to remember theorem 5.10. In fact, why I'm doing compactness now, I think next week before Diwali, look, you have page 175 to 176. The next note, note 19, I have given problems that you have 7 problems. Yeah, I think 7 problems, but these are all important problems. So make sure that the next week you ask Bhavna and Dhiraj to for discuss the problems on that. Okay, so that here, so characterization, I'm coming here, theorem 5.10. So proof is immediate. Basically, proof depends on theorem 5.10, and that's why I did this 5.8, 5.9. So this proof now easy because of this. Okay, now look what it says. It says you take a metric space and you take, look, finite subset is always compact. So we do not need to bother about this finite. So I am taking infinite. Okay, its characterization. Since the following are equivalent. Following are equivalent. A is compact in Xt. Since A is itself infinite, so it makes sense to state B. Every infinite subset of A has an accumulation point in A. Look, it has to be in A because if I assume it is compact in a Hausdorff space, particularly in a metric space, every compact set is closed. And accumulation point is a particular type of closure point. So if A is closed, then that accumulation point has to be in A. That's why you need this. Okay, and C, look here, every sequence xn in A has a subsequence, look, converging to a point in A. Again, because A has to be closed, point in A. This is required. Because if you are because of the definition of the result on the closure point, if you have a sequence in A converging to a point, since it is coming from A, so that limit has to be a closure point, but A has to be closed if you are trying to prove A is compact. So it has to be this. Okay, now by using theorem 5.8 and 5.9 we can prove it. Okay, you should read the proof. I will give you that. I can give you the proof, but right now I want to discuss the applications and that. Okay, so this is very important. You'll have to. First, you should try the sequential characterization. This is what I told you, sequential characterization of compactness. Okay, so this is whenever you are dealing with something subsets of metric space and whether it is compact or not, first you should try it. If it doesn't work well, then you should go here. Okay, proof. Look, basically theorem 5.8 and 5.9 I have proved everything on that. Okay, so that I will prove it later on that, but you should, whether you understand or not everything, you should read the proof of that. Okay, theorem 5.8 and 5.9, first read the proof of this. You should not have problem. This uses, in fact, one part is exactly like B implies C. This is exactly theorem 5.9. Okay, right. But A implies B, that's very straight. You should prove it. Okay. If you do not have it by negation, then A won't be infinite. Okay, right. So that you should look at the proof. Okay. And look, C implies A also, you should see that. Also here you see that every sequence has a convergent subsequence. Here is the difference with the total boundedness. Total boundedness only gives me a Cauchy subsequence. So that's why compactness is stronger in total boundedness in a metric space. It has a convergent subsequence, whereas totally boundedness you have a Cauchy subsequence. But the point is that if you are dealing with a complete metric space, then any Cauchy sequence will converge. Any Cauchy sequence will converge. Then total boundedness and compactness should coincide. That exactly the theorem 5.11. Theorem 5.11. Look, theorem 5.11, what I am saying. A metric space, this is very important. Xt is compact. Look, compactness is only relation to the open set, topological thing, whereas completeness is a metric thing. Both completeness and total boundedness is a complete. If and only if Xt is complete and totally bounded. Look, I will use sequential characterization and compactness. Look, suppose you are assuming, basically you need all sequential characterization. Suppose Xt is compact. Okay. Now I need to prove this is complete and this is this. Okay. Well, you take a first Cauchy sequence. Let Xn be a Cauchy sequence. Look, when you are taking the whole space is compact, then accumulation point in A and that will be automatically happen because that will be in X because everything we are working inside X. Okay, let Xn be a Cauchy sequence in X. Then by the sequential characterization, look, every sequence has a convergent subsequence. So the Xn itself is a sequence in X. So by sequential characterization, by C of the previous theorem, of theorem 5.10, sequential characterization, Xn has a convergent subsequence. But I have proved long time back that if a Cauchy sequence has a convergent subsequence, then Cauchy sequence itself will have to converge because Cauchy sequence members are getting close to each other. And here, these members of some subsequence, they are getting close to some point. They are gathering towards. So ultimately, the members of this sequence will have to, after a while, they'll have to close to gather. They will have to gather to that point, around that point. So it is convergent. So Xn is convergent. Okay. So that Xt is complete. If every Cauchy sequence has a convergent subsequence, then that Cauchy sequence converges. That I proved long time back. Okay. I did it for real line. I said in the metric space the same proof works. Okay. Right. So this is complete. And totally bounded also immediate because totally bounded you'll have to use that result. Every sequence has a Cauchy subsequence, but here every sequence has a convergent subsequence. So automatically it will have a Cauchy subsequence. So if this proof is you are using sequential characterization of that. Okay. Now the other way, Now look. Other way looks, if you have complete and totally bounded, you'll have to show that this is compact. Again, you will use this thing. This is importance. Okay. So take any sequence. Let sun be a sequence in X. Okay. Right. Now it is totally bounded. Look at this. So it has a Cauchy subsequence. Since xt is totally bounded, xn has a Cauchy subsequence. Xkn. But this is given complete, so it converges. Okay, right? So that you are getting every sequence has a convergent subsequence. I am using this thing, sequential characterization. So any metric space is compact if and only if it is complete and totally bounded. Now look at the difference between compact and totally boundedness. This is the big difference. Don't forget that. Okay, you need completeness in that. Now look, I said that. So theorem 5.11, look at the proof. I am using only basically this. Okay. Here everything in terms of the sequence. That's why I'm using this. I put a remark here. Now let me tell you the remark. Remark is very important. So that what the remark I said. Look here, you remember if you that minus pi by 2, here the usual distance is not complete. Okay. But I could give another metric d by arctan x. Remember that. Another metric d is equivalent to that exactly I have discussed here. Equivalent to this, but d is complete. But look at the previous theorem. Xt is compact. This is a topological thing. It is only involves open sets. It's compact if and only if xt is complete and totally bounded. Look, this is if you take another equivalent metric rho, suppose x rho. Suppose this is equivalent. Equivalent means what? It gives you the same topology, but compactness doesn't change with the open if the open sets remain same. So that xt is compact if and only if x rho is compact. If you take any equivalent metric, then xt is compact, then x rho will be also compact. Equivalent metric means they generate the same topology. Compactness is actually the topological thing, definition. So this will be compact. That means again by this result, x rho is complete and totally bounded. Look, complete and total boundedness depends on the metric. That means if you have a compact metric space, it doesn't matter if you take another equivalent metric, that will have to also be complete and totally bounded. That means if it is not compact, then this kind of anomaly happens. Look, here what I am getting. Here this is complete, so it is equivalent metric. This is not complete, here complete. Why this anomaly is happening? Because this is not compact. So that means if you take this is complete. This is totally bounded. If you take another metric equivalent to this, another metric here, suppose sigma you take, equivalent to this metric will be also complete and totally bounded because this is compact. So that is the importance of another importance of compactness. If you have a compact metric space, it behaves very well. That look, if X is a compact metric space, then the equivalent matrix will have to behave in a similar fashion. That means compact matrix space will have to be complete and that. So another metric equivalent matrix you take, that has to be also complete. I have talked about this in the remark. So that here your job is that theorem 5.10. Read the proof again, I am telling you. Okay. Read the proof carefully. Reason is I am telling you why you should read the proof and that. If I get time, I will do it. I will talk about the proof because here you need to learn some technique here. Otherwise, you won't be able to solve the problems. Okay. And while first you read theorem 5.10, okay. Read the proof. And then I am just saying that you read the proof of this also. You don't need to mug up anything. Whether you see that if you understand the proofs. If you do not understand the proof, you can ask me, you can ask the tutorial teachers, you can ask Bhavna, you can ask Ziraj. You should ask. I'm saying you don't mug up. This is you think of just a tutorial problems. You read the proofs. First you read the proof of this. Here we are using this. Okay. And somewhere if you do not understand, you ask. Because reason is that here some techniques are involved. Those techniques you need to learn. Okay, right. Make sure that you do it. Okay. Now I want to finish it, but before leaving, I am telling you that you should now read. Next time I will do note 19. You just see that. Yet note 19 basically I have Heinborough theorem in that. Okay. And also, of course, I talked about Lebesgue number and that. Okay, so but main thing is that here I talked about an elementary proof of Heinborough theorem. So I am giving the proof of Heinborough theorem, an elementary proof, by using Cantor's intersection theorem. If you use sequential characterization, that you can easily prove, but you see that to get this result, I needed these two big results. So how much I had to work hard to get this theorem, and then by using this theorem get Heinborough theorem, proof will be easy. But again, that you should look Dali-Francis Birkinshaw. But the point is that apparently the proof is not easy because पीछे बहुत result है which are using. Here Heinborough theorem I will be using the simple result and Cantor's intersection theorem. Okay. So Monday, of course, I will take the class. Monday is October 25. I'll take the class around 12 noon. Again, this time 12 noon I'll start. Okay, so this is very important. Heinborough theorem. Note 19 I'll do that. But again, you see that next week the tutorial I will prefer that you ask Bhavna and Dheeraj for extra tutorial to finish compactness. Because whatever you need to do the problems that I have taught you, including the Heinborough theorem, the statement you need, that page 175 and 176, the problem I have talked about. Okay. And also, you should look at the last year's major questions papers. Well, let me tell you that. The major will be 60 marks. Well, let me tell you that here what I will give you. This compactness will play a big role. It will be at least 40%, I think. Then I'll give the Bayes category theorem problem. I'll give you one problem in connectedness that I'll teach you. Though I will teach connectedness in detail in the next semester, but little bit connectedness I will teach, and one problem I will give on this. And here, equicontinuity. That's the note 2021, I think. Equicontinuity. In fact, Monday I want to finish this Hahn-Bodel theorem, and then Tuesday and next Friday I will teach you this equicontinuity and connectedness, particularly equicontinuity, then connect, so that this will be 40% minimum. So another 60% will come from here. So roughly you can say that 20% each. But there will be some variation, I think, because if it is 50%, then it will be less than that. So compactness, it may be even 50% also. Okay. Okay. Connectedness, what I'm saying, probably it will be 8 marks. Okay. Right. So it will be, if I put 30 marks, then I need to prove some 12, 8, 10 marks or like that. It will be briefly like this and that. So compactness is very important. It may be even 50%. Okay. Because compactness is a big concept, both in analysis and topology. You need to learn in mathematics overall. So you need to handle compactness. Even if you start with a nice metric space, and that it's not easy to handle compactness. Even if you want to handle compactness in a metric space, you need to learn many theorems like theorem 5.10 and Hahn-Bodel theorems. So next time, Monday, I will teach you I will give you the proof of the Hahn-Bodel theorem. Okay, right? Okay. See you on Monday. Okay, bye.